Okay, in this video I'm going to talk about what torque is and how it causes the rotation of objects. So if we have some object, I don't know, a rock or something, if we consider how its mass is distributed, there'll be some point in the center of the object that represents the center of mass. You can almost view this as the average location of the object. So if you took all the mass and you took the average and you pinpointed one spot, which right at the center, that would be what this point is. Now imagine that there's a force acting on the edge of this rock right here. What that's going to cause, because this force does not pass through the center of mass, is it's going to cause the object or the rock to rotate. The amount of rotation will depend on two factors. One, the size of this force, and two, the distance from the force to the center of mass. We can imagine, for example, if we had applied a smaller force closer to the center of mass, we would have had less rotation, and when we go all the way out to the edge of the object and apply a big force, we get as much rotation as possible. In physics, we talk about the combination of these two factors as the torque acting on the system. Torque is equal to the distance from the center of mass to where the force is applied to the object, R, and that's this R right here, from the center of mass to where the force is applied to the object, times the force. There's one more thing here. I'm going to try and draw this separately now. And here maybe that's about our center of mass. And that is, if we apply a force, I drew this force at a 90-degree angle to the distance from the center. But if we apply this force on some funny angle where it's not, where some of it is directed beside the object and some of it's directed along the object, what we can see is only some of this force is going to cause rotation. Only this part here. This part is in line with the center of mass, so it's not going to cause any rotation. It's only this little part that's going perpendicular that's going to spin this object. So it's not simply the radius and the force, but it's the part of the force, or the component of the force, that's perpendicular to the distance to the center, or the part that can cause it to spin. For that reason, if we want this part, and this is theta, then this component is the sine. So it's the F sine theta, where theta represents the angle between the force and R. So here we can see this is going to cause as much rotation as possible because it's at a 90-degree angle, and if it came straight in here at a 0-degree angle, it would cause no rotation. And then we can imagine somewhere in between where it comes in and only this component of it is causing rotation. And if I imagine then using a Z pattern, this theta or this theta, it's the sine of the angle that gets us the component that's pushing it to 90 degrees and causes the object to rotate. So that's what it is mathematically, and sometimes for torque we shorten it to the scripted Greek letter tau, which just looks like a T with a slanty top on it. And there's no special unit for torque. So when we do torque, we have newtons and we have meters, and we just leave it as Newton meters. We don't bother changing it into something new. We do not, even though a joule is a Newton meter, we do not use joules for torque because we don't want to confuse work and torque. They're different things. From a practical standpoint, we can imagine one of the main reasons or one of the main advantages we get out of torque, which is the idea if we have something like a nut. Now, if we imagine trying to apply a force to this nut to get it to rotate, because the nut itself needs to be pretty small, probably for the design of the material that the thing is in, or the design of the piece of equipment that's using the nut, we want it to be pretty small, so we can only get a really small r. So our torque, which is equal to Rf sine theta, but we're going to assume for the sake of this argument we're applying the force at 90 degrees, so sine 90 is going to go to 1, so we're not really getting concerned about him. You're going to have to apply a really large force because your radius is really small. One way that what that might mean is that you can't apply enough force to that small bolt to make it turn enough. So what you can imagine doing is extending your grip on this with something like a wrench. And then when you apply your force at a much larger distance, the force itself can be much smaller. So the wrench extends the arm over which, or extends the length over which the force can be applied greatly. And what that means is not only does it allow us to get a piece of metal or something that we can get a better handle on and actually apply our bigger force, but it means the actual force required to rotate that object is going to be much lower because we've increased the separation distance. So that's what torque is. That's what causes the spinning of objects. Those are the factors that it depends on, R, and then the component of the force is perpendicular to the R. And that's probably the most obvious way that we use torque to our advantage, is by extending the arm that we're using to push on objects so that we can lower the force required to rotate them.